Okay, so I'm not gonna wait any longer for Andrew, so we're gonna just get started over here as soon as I find my pen. Uh, so please put your name and period. Please put your name and period. Can you guys see that in back? This is gonna be new for me. I gotta practice writing. Name and period across here. And next. Okay, so we're talking gases. Well, this doesn't work here. Or it doesn't work there. Come here. Come here. There we go. We're talking gases. This is traditionally a fun unit, guys. Define fun. It's not too hard. The math's not too hard. It's kind of plug and chug. There's a lot of fun demos next class, and then you guys get to demonstrate a gas law of your choice.
Is the test gonna be multiple choice?
And there are no more multiple choice tests. So a couple things we got to point out. Remember, the particles are very far apart when we think in comparing the three states of matter. So in this room, there's a whole bunch of gas particles, but they are really far apart. And they have the greatest, that they're moving very fast. They have the greatest kinetic energy. So remember, kinetic energy is literally the speed of the particles. Now you can say, well, it's not real hot in here, but they're still fast moving particles. They're way faster than the ones in your body are moving. In your body, you can think, oh, but this, I'm at 97 degrees or whatever. And the room is not. That's how far apart they are. If you kind of, can you kind of feel the difference? That might not be a good way.
I get that.
They're just so far apart. They collide. We saw this already with collision theory. Every collision exerts a little tiny packet of pressure. And the more collisions, it says here, the greater frequency of collisions. So this is over time. Frequency has a time contingency part of it. The greater the pressure of the gas. So just in general, keep that in mind. This is a review of temperature. It's the measure of the average kinetic energy or movement of particles. So we use a thermometer to measure the average kinetic energy or movement of particles. And the liquid inside the thermometer is sensitive to the collisions that are occurring through the glass and into the solution. Faster the particles of a gas move, the higher the temperature. Now that's for gas samples, but it's also for solids and liquids. The faster the particles are moving, higher the temperature. Now it says here, gas particles move independently of each other. That is different than we see with liquids and solids. With liquids and solids, you have these intermolecular forces, right? Liquids, you've got those hydrogen bonds that are breaking and reforming that allow this tumbling to occur. Solids, you have a locked in lattice structure that kind of vibrates. But gases, one gas molecule is moving completely independent of another gas molecule. So there's no effect on each other until maybe they happen to bump into each other. And then it's super fleeting. And it's, so independent of each other. Then this goes on to tell you that pressure and volume are inversely related. If one increases, the other one will decrease. So we've talked about this relationship before. And it's usually represented with that piston, the little piston drawing. This is pressure times volume equals a constant. So basically, all this is telling you is that for an inverse relationship, you're going to multiply the two variables together. You multiply the two variables together for an inverse relationship. Does that make sense to you, everyone? And then it says in a closed system, this relationship is true in a closed system. And we're going to assume closed systems in this unit. Number of moles of a gas does not change in a closed system. So you'll see a lot of balloons, you'll see a lot of containers. Because if it's not a closed system and you increase pressure, basically the gas molecules just move away, right? Does that make sense? They just go somewhere else. Yeah. Okay, cool. This can be shown graphically. Can you guys already draw this graphically? Pressure and volume being indirectly related? Yes or no? Do you think you can? So if you have two axes, one pressure and one volume, what is indirectly related? Like that? Yep, pressure and volume. Sorry, this is still in a way. So when you have a sample of gas in a closed system, changing one variable results in a corresponding change in the other. Remember, this is a closed system. So we get this relationship, pressure times volume equals pressure times volume. This is going to happen because of this constant here. Now, what this is explaining is changing one variable will correspond to a change in the other variable. This is just an example of pressure and volume being the two variables. But again, in a closed system, we can have other variables that equal constants. We know their mathematical relationship, they equal a constant. And then in a closed system, we can set them equal to each other. Does that look familiar? That little mathematical relationship look familiar? Yeah, so hopefully this isn't too difficult. This is an example question that's worked out. Then we have temperature and volume are directly related. So here we have volume and temperature directly related. What would this graph look like? Volume and temperature. Boom, right? Direct relationship. And they're directly on top of each other, so they're divided. Now, in a closed system, can you kind of guess? The moles of gas does not change. What this is going to look like? We look at the previous one. In a closed system, we could set the P and V equal to the P and V. This is initial and final. So in the next one, if we have a VT equals a constant, we can set it equal to a VT, initial and final. That makes sense. Now, what happened to pressure? If pressure is not in the relationship or in the graph, then you always assume it's not changing. So you might go with here, we're only looking at pressure and volume, so you can assume temperature is not changing. You can assume temperature is not changing. Yes.
So if pressure is a function of volume and volume is temperature, sorry, why can't you do pressure as a function of temperature?
You can.
Yeah.
Yeah, you can, but in these graphs, you're going to, when you're comparing the two variables, you assume that the third is not changing. Just that, yeah. Assume that the third is not changing. So pressure, volume, and temperature can be measured in a various number of ways. So couple things. You must memorize the following equalities. And this is straight up, this homework tonight. You want to memorize this. Pressure is a measure of the number and force of collisions. The force comes from the speed and size, right? And 1 atmosphere we discussed already. That's how much at sea level all the gases are. Well, that is the same as 760 millimeters of mercury, which is the same as 101.3 kilopascals, which is the same as 760 torr. So you need to know these numbers as they're interchangeable. Meaning, if I told you the pressure today is 730 torr, oh, that was lovely. Can you convert it to kilopascals? Yes or no? So what you would do is you could use dimensional analysis. You're going to write 760 torr on the bottom. So you can cancel out that. And I asked for kilopascals, so you go 101.3 kPa. Right. Then you cancel torr, and you're left with kPa. You multiply 730 times 101.3, hit equals, divided by 760, and you've converted to kilopascals. So need to be able to convert between these guys. Volume. You should be pretty good at this. Don't forget a cubic centimeter is the same as a milliliter. Don't forget those two are the same. And a decimeter cubed. So a decimeter cubed, deci means 10, right? So it's like 10 times 10 times 10. Right, a decimeter cubed, because the decimeter is 10 centimeters. Yeah, so that's where you get it. Just a unit of volume. And temperature, in this unit, it must be expressed in Kelvin when using the gas laws. Always have to change it to Kelvin. We ready to get started? Yay, come on, it's gonna be fun. This is our first gas law. Is there a way to hide this sucker? Ooh, what's that? Sorry. So we're looking at those pistons. This is Boyle's law. You are going to have to know it by name. Boyle's law, come on, let me try to underline that again. Boyle's law. And what we're looking at, this is a thermometer. And notice the temperature is the same on both, right? And the volume here, here's your little piston. It's pushing down or pulling up. So our volume is this blue here. The volume does change. So we know that V is one of our variables. And you can look at the pressure gauge. It doesn't tell you what this is, but it looks like atmosphere, 1.0 to 2.0. So this is volume and pressure. Pressure being 1 and volume being 4 equals pressure being 2 and volume being 2. Does that make sense? And is that a correct statement? 1 times 4, is that equal to 2 times 2? Yeah. So in a gas, pressure and volume are how related? How are they related? Inversely. When temperature is held constant, as pressure increases, volume does what? Decreases, and as pressure decreases, volume increases. What do you think? Pretty straightforward. So let's try a problem. It says here, if a gas at 25 degrees Celsius occupies 3.6 liters at a pressure of 1 atmosphere, what will be its volume at a pressure of 2.5 atmospheres? So best thing to do, I find, with gas law problems is to just label the variables. 25 degrees Celsius, that is a temperature, right? 3.6 liters, that's a volume. It gives me a pressure of 1 atmosphere. And it's asking what's going to be the volume. This is the second. So I'm looking for V2. That's my second volume. And this is my P2. That is my second pressure. Now, if we look back here, this is our initial and this is our final. So Boyle's law is P1 V1 equals P2 V2, right? So this is Boyle's law. That's Boyle's law. Oh. We're given temperature, but it's just one temperature. So that means it's staying constant. We have a volume and a pressure, and it's asking for another volume with another pressure. So this is just plugging and chugging into Boyle's law. Make sense to everyone? So what do you guys get when you plug and chug? 3.60 liters. You're going to multiply that by 1.00 ATM. That's going to equal volume 2, which we don't know, and pressure 2, 2.50 ATM. To solve for that, we're going to divide this side by 2.50 ATM. That gets rid of this. And then notice the ATM will cancel because they're over each other. So we're going to be left with liters for our units. We look at sig figs. We got 3 sig figs here, 3 sig figs here, and 3 sig figs here. So there'll be 3 sig figs in my answer. What do you guys get? 1.44 liters. 1.44 liters. What do you think? Pretty simple, right? So then let's switch color. Oh, come on, just show it here for this one. Let's do it again. A gas occupies, this is volume, at 0.086 atmosphere, that's pressure. It's asking for pressure. What will the pressure be? So P2, if the volume, this is V2, is 15 liters. Now, just using our knowledge of the law, is the pressure going to be more or less than 0.86? Because the volume is greater. Does that make sense to everyone? So keep that in mind when you're doing math, just to double check yourself. So 11.2 liters, 0.860 ATM. Looking for P2, and we know V2 is 15.0 liters. How many sig figs in my answer? All right, 15.0 liters. That cancels this guy out, and my liters cancel. So I'm left with atmosphere. And what is my pressure?
0.642 atmosphere.
Okay, 0.642 ATM. Is that what you guys got? And it is less than 0.86 ATM. Pretty straightforward, right? Save the next one for your test review, obviously, for reviewing for the test. Let's check out Charles' law. Notice the size of the flame here. Here we have temperature that changes, which then changes the volume. And then down here at constant pressure, it says here volume, liters or milliliters or cubic centimeters or cubic decimeters, and temperature in Kelvin have a what type of relationship? Direct, right? Direct relationship. So this Charles' law is V sits directly over top of T equals V sub 2 directly over top of T sub 2. So you can think of 1 and 2, initial or final. Want to do some more? Pretty straightforward. Okay, so a gas occupies 1 liter, that is volume, at 64 degrees Celsius. We don't want Celsius, so cross that out. And what do we add to 64? 273. 273. So this is 337 Kelvin. It's asking for V2, not at 330. I get 603. 603 Kelvin, right?
What about 0.0?
Yeah, because I added, yeah, you can keep the 0.0. Absolutely. I was looking ahead to the end. The reason I don't have to keep it is I know my sig figs are going to be less than that. So that's why I dropped it off. But so then we're just putting it into the formula. 1 liter over 337 Kelvin equals what over 603 Kelvin. Now remember how to do this. You're going to cross multiply. Does everyone remember how to cross multiply? You're going to have 1 times 603. It equals, and then you'll divide by 337. This, then this. You guys remember how to cross multiply? Because this is really, then you multiply these two, hide this. You get 337 times V2. To get this out of there, you divide both sides by it. This is Kelvin, this is Kelvin. My Kelvins cancel. I'm left with liters for my V2. What do we get? I'm sorry? 1.79 liters. This is only 2 sig figs.
So we use the sig figs from the original in the Celsius.
Okay.
Okay.
Because what this means is this thermometer was weaker than this thermometer, right? So this thermometer didn't even have a decimal place to estimate to. So we're only as good as our weakest thermometer. So 1.8 liters would be. 4.8 liters. Whew, it is not easy to write like this. Can you read it though? Want to do another one? Okay, why don't you guys do it yourself? And I will do it off camera. There is no off camera. You guys get 268 Kelvin? We're golden. We're golden. Okay, let's start moving a little faster now. Gay-Lussac's law. If we look here, we're looking at the same number of gas molecules. So same number of gas molecules is kept constant. Here we have different temperatures and we're measuring pressure. We're measuring pressure. Here's Gay-Lussac's law. Pressure is directly related to temperature. You increase the temperature, you increase the pressure. Make sense? So we're trying to find pressure. So we're looking for P when a constant volume of the gas at, this is pressure, is heated from not 20, what is this? 293 Kelvin to 303 Kelvin. Right. So here is temperature 1 and here is temperature 2. So how are you setting this up? You should have your 1 ATM over 293 Kelvin. Set that equal to the pressure you're looking for over 303 Kelvin. So you're going to do 303 divided by 293. What do you get? What?
1.03.
So 1.03 ATM. Look at that. It goes up by 10 degrees Kelvin. The pressure only goes up by 100, 300. It's kind of a neat relationship. Okay, I'm foreshadowing. Now, we can combine them, what we've just learned. Notice the combined gas law. What was P times V equals P times V? Who was this? Boyle. That was Boyle's law. And then V over T and V over T, Charles. And then I don't have another, oh yeah, I do. And then P over T equals P over T. Who was this? Gay-Lussac. So if we put them all together, it's called the combined gas law. Totally makes sense. Combined gas law. Now, these are easy to spot because you have to be given 1, 2, 3, 4, 5 variables and be asked to solve for the sixth. So any problem that ends up giving you 5 variables, you know it's going to be the combined gas law, because the hardest problem you're going to have with these gas laws is knowing which one to use. Just knowing which one to use. So 0 degrees Celsius is 273 Kelvin. That is a temperature. 1 atmosphere is a pressure. A sample of gas occupies a volume. If the temperature is increased to 303 Kelvin, and the entire gas sample is transferred to a 20 ml container, this is volume 2, this is temperature 2, and it's asking for P2. So we just need to plug and chug. My first pressure was 1.0 atmosphere. My first volume was 30.0 milliliters. My first temperature was 273 Kelvin. Then they tell me the temperature increased to 303. The volume is transferred from 30 mils to 20 mils. And it's asking for pressure. Now, to solve for this, we're going to flip this and continue it over here. So you extend this line, and this is going to go on top, 303 Kelvin, and the 20 mils is going to go on the bottom. So you're flipping this over here. So in your calculator, you'll multiply all of this, hit equals, and you'll multiply by this, hit equals, then multiply by that, hit equals. Keep it all in the calculator. So this is an important relationship. When you look at it, this is setting it up, well, temperature, so you would think volume increased, but then they lowered the volume. So you can't directly relate to pressure. So it's not something you can easily guess whether it's going to be greater or less than the previous pressure. What do you guys get? 1.7 ATM. Did everyone get that? Combined gas law. Combined gas law. Next. Last page. You want to try this one on your own? Otherwise known as page 13. We're just going through page 13. Label, we have a pressure, we have a volume, and we have a temperature. It's already in Kelvin. The pressure and temperature are changing. So we have a pressure 2 and a temperature 2, and it's asking for our volume 2. 12 ATM, pressure. 23 liters, volume. Whoop. And 200 K equals 14 ATM. I'm looking for volume 2 over 300 Kelvin. Again, to solve it, again this. Put the 300 Kelvin on top. Put the 14 ATM on the bottom. It's to go away here. Flip it. Keep it all in your calculator. How many sig figs?
One. Because the
300
300 Kelvin. and-
Yeah, it's 1 second.
And 200 Kelvin, yep. 300 times 12 times 23 equals, divided by 14 equals, divided by 200 equals. So we get 30 liters. Sound good? Awesome. So you can save that last one for test review, but you have your first homework. I'm gonna end up calling you start a new habit. Beginning of the word order. That's okay, if you're planning on being back. They're reverting back to pre-COVID policies, which is nice.
So we're gonna get like regular signage next week.
Yeah, for the whole year, but they're gonna have your code on, it's gonna be how you check out things at the library, it's gonna be how you do all kinds of stuff. Well, last is due next class,
Oh, yeah.
I want you to focus on showing your work. What I mean is, I want you to show me where you're putting. Way longer to do it than my way.
I'm just having- yeah. I like that.
Yes, and paper. Now, what you might want to do is go through and convert all the temperatures now, so you don't forget. You can go through every one, look for Celsius, cross it out, and put Kelvin. I didn't give you one?
Oh, yeah.
What?
Oh, yeah, yeah, I didn't know.
Are you sure? I was just there. Now, I'm one of like 8 teachers that are going to pilot a electronic task system next week.
It's just spiraling down.
No, this is super cool.
Wait, what?
Basically, you write your own tasks. I did training before break, and we're gonna start it next week. There's an app for your phone where you write your own tasks. Right, let's say you wanna go to the bathroom.
Not with my shutting down phone that will shut itself down. I'm getting a new phone, but
Okay.
That's an awesome.
I like it. And then I just have to put in my approval code. go, we say you're gonna go, and you come back, and I just say you're back.
So they want you to bring your phone now?
Huh?
They want you to bring your
Right.
phone.
Yeah.
Instead of.
Wait, does it have like a GPS tracker? Like,
Yeah.
that would be-
That would actually kind of help me.
Low key.
No, like when you're that one that's.
Yeah, the one person I got for 20 minutes, you can check where they are on the system.
So they should have this number, like, vibrates your phone, like, really loud, goes,
Or
get
like-
back from
or
the
like
bathroom.
zaps them.
After it takes so long. Like,